Now you have to answer, this meeting is being recorded.
Can you hear me actually? Can you hear me?
I could hear you earlier.
Now how about now?
Oh, no, I didn't know.
Now in the Zoom you cannot hear me, right?
Yeah, I can.
You can? You can still hear me?
Yeah.
Okay, cool. Hello, good morning.
These are dim the lights. Front lights. We're doing that.
No.
Maybe these lights here. Try no, not one of those are opening the door. I think let's just try two. Good.
Okay.
First time lucky. Good morning, everyone. It's the last day, but we've got to start on time. That's the rule. So today is the last day of the meeting, but we've saved the best for last. It's over. And so I've got some superb speakers today. And we're going to continue with our tradition of asking lots of penetrating questions to the speaker.
Sure.
And today we have a novel innovation. Everyone who asks a question gets a chocolate. Okay. You've taken one in advance, Circa. That's not.
And now you have to ask the questions.
I'm sure she will. Since we're kind of closing out, I just want to I want to reiterate my thanks to everyone who's helped make this meeting possible, including the folks at UCL who aren't quite here yet. Frank and Andrew Green, without which we wouldn't have these rooms. And Andrew Ho, who is diligently is going to be in contact with you all concerning reimbursements. My mind's going to a blank. Sam Carr, who has helped with all the students. Jorge Intermedia, who's also provided moral support. And Gunnar, who has been our webmaster, absolutely magnificent. And
Pierce.
yes, yeah, thank you, Pierce. Thank you, everyone. And God willing, we will rise again and have cadets banter in the city in a year's time. So to be sorted. Well, in the meantime, it's our great delight to have Fai Mak. Kin is jointly for the moment, both on both sides of the pond. He's at Cornell and he's also on his way to, or is already at Hamburg. He's in a mixed state, I guess. In fact, he's not halfway across the Atlantic. He's both on both sides of the Atlantic simultaneously. This is just his image on this side of the Atlantic. There's probably an exact similar one in Ithaca. We don't know. Anyway, so thank you for coming today. He's got some wonderful work on Moiré and strange metals, and we're just dying to hear about this new result. So thank you very much.
Okay, thank you very much for the kind introduction and for the invitation. Come here. Great pleasure to attend this workshop conference and also be in London. This is actually my first time, although I'm from Hong Kong. Somehow this is my first time in London. So I'm going to talk about some results on trying to mimic the high TC phase diagram in a triangular Moiré lattice. And before doing that, I would like to really acknowledge people doing the work. Most of the work was actually led by a fantastic graduate student, Jie Shan, and also a postdoc in our group, Zhong Donghan, and also with assistance from two additional graduate students, Yi Zhang and Weimin Zhu. And as many of you know that we share labs with Professor Jie Shan, now still at Cornell, but we are on our way to Hamburg. And boron nitride crystal is always from this famous Japanese group from NIMS, Kenji Watanabe and Takashi Taniguchi. And here are the funding sources. No, actually, I should update the funding sources because it's been taken away. Well, I think I probably don't need much an introduction, but I still just give very brief introduction. We're trying to study, as I said, we're trying to use a Moiré system to mimic the phase diagram of high temperature superconducting, in particular the cuprates. This was discovered in 1986. It's just not that the TC is very high in this material, but also the fact that the phase diagram is complex and very interesting. So we start with a Mott insulator with no filling. And then you dope the Mott insulator, you get antiferromagnetic state, then you get the superconducting domes coming out. But the more interesting phases are probably more in the normal state, is including this pseudo gap phase and also the strange metal phase. And soon after this discovery, it's really like a few months or less than a year later, Anderson actually proposed the strong correlation viewpoint that the essential physics could be captured by the Hubbard model. With these two terms on a square lattice, the T and the U. Okay. And how can this simple Hamiltonian give rise to that kind of complicated phase diagrams? Because the two terms in a Hamiltonian just sort of tell the electrons to do opposite thing. One is to tell it to delocalize, to gain kinetic energy. One is to tell it to localize, not to have Coulomb repulsion. And so the physics of this model is governed by the ratio, the U over T or the U over W. W is the bandwidth for a square lattice is A times T. Okay. All right, so Mott transition for when U is very small compared to the kinetic energy at a half band filling, meaning on average 1 electron per unit cell here, per site here, then you just get the Fermi level cutting at half of the band, and you get a very good Fermi liquid or metallic state in this limit. In the opposite limit, then of course, the electrons are localized by the Coulomb repulsion, and all the electrons are now localized on each side, and only the spin degree of freedom is left. So in this large U limit, pretty much that energy gap on the order of U is open at the Fermi level. And Mott proposed that, somewhere in between, if you can tune the U or the T, somewhere in between, you can get a bandwidth tuned Mott transition. Okay, and how is this related to ITC? Is again Anderson's idea that a weak Mott insulator near the Mott transition is probably a resonating valence bond state. I think Shane has already talked quite a lot about this. It's RVB state. I think I don't need to introduce what RVB state is because many people know much better than me. But the essence is that the wave function is like a BCS wave function, but without double occupancy, so that it makes sure that it's in the Mott insulating state. So the pairs are already there, but they are not free to move. And once you adopt the RVB state, you free the pairs, and then you get a superconductor. So that's sort of the idea. Well, in a square lattice, it's probably hard to get an RVB state because there's no frustration. Well, you can probably add some extra frustration. But it's more natural to get antiferromagnetic state in a square lattice. But in a triangular lattice, it's actually more natural to get a spin liquid state because of the geometric frustration. And indeed, there are some quite recent numerical study that suggests that in a U-tuned metal to insulator transition on the triangular lattice, in this triangular lattice Mott transition, very close to this critical point, the Mott insulator could be non-magnetic. In fact, it's a chiral spin liquid. That's what they propose in these studies. And then if it's a chiral spin liquid, if you dope the chiral spin liquid, you get superconductivity naturally. And these are additional numerical studies, quite recent also, to show that you can get superconductivity by doping a chiral spin liquid on the triangular lattice.
Just to make a comment, there's an urban legend going on here about spin liquids and RVB. I just want to point out that actually the spin 1/2 antiferromagnet in 2 dimensions can be described as an RVB state, something that the Anderson group itself discovered. And so there's a deeper subtlety here than just singlets fluctuating, because an antiferromagnet can be written down as a fluctuating combination of singlets. In fact, the 3D antiferromagnet can be described as just very short range nearest neighbor RGB state. So something deeper about the kind of.
Yeah, I guess, but just not this long range.
That's right, the long range one, and it's also the phases that matter, the way the phases between the different linings matter a lot.
Okay,
So there's a lot of subtlety here, RGB and spin liquid aren't necessarily the same.
as I said, the audience knows a lot better than this thing.
That was the statement, well, I don't get a chocolate for that. Can I?
It's not a question, it's only a comment, yeah. Okay, so that's my very general introduction. It's promised to be short, and then I'm just going to talk about, it's good to have an experimental system that can mimic the Hubbard model and see whether this idea of that most of the phenomenology can be described by Hubbard model. And actually, that's one of the goals from in the AMO world, that they have very nice Hubbard model simulators. In fact, it's nearly exact in their case, so they can trap atoms in the optical lattice. They can tune the filling, not as well as the Moiré materials, but they can also tune the interaction. And the interaction is really short range in this type of system. So they're trying to use one controllable quantum system to simulate the phase diagram of the Hubbard model. The difficulty in that kind of situation is that it's very hard to actually cool it down the relevant temperature to really see the High-Temperature phenomenon. And of course, there's a new class of materials these days. It's the Moiré materials. The most famous is the twisted bilayer graphene, and it's first actually found by is it accidentally, or I don't know whether it's accidentally or not, by STM experiment, Levi and Bray's group. But unfortunately, they didn't observe superconductivity. It's later on that from Pablo Herrero's group, they observed superconductivity about 8 years later, and that really triggered the field to grow. Okay, so this is the band structure of the twisted bilayer graphene. I'm not going to talk too much about twisted bilayer graphene. But it turns out that actually it's quite complicated in the twisted bilayer graphene, because you have the two bilayer degree of freedom, you have the spin and valley degree of freedom. There are just too many degrees of freedom in the twisted bilayer graphene. And the correlated insulating state here is also not really like a conventional antiferromagnetic Mott insulator, and the bands are topological. So it's quite, it's quite far off from the Hubbard model in that case. It's in simple one band Hubbard model in that case. Okay, so it's nice to actually have a different system that really gets pretty close to the single band Hubbard model in these Moiré materials. And that's why I'm going to talk about the TMD semiconductor. So this is the structure of a monolayer TMD. You look from top down, it looks like graphene, and the electronic states are also like graphene, located at the corners of the Brillouin zone, not at the center of the Brillouin zone. So it's actually quite different from most semiconductors that you're familiar with. Mostly they live near the gamma point, but here it's living at the K and K prime point of the Brillouin zone. This is the zoom in band structure near the K and K prime point. They're just two copies of the direct energy gaps. K and K prime, the intrinsic material is that the Fermi level is inside this big gap. It's about 1 to 2 electron volts. Okay, and there is also large spin-orbit interaction in the moly and tungsten compounds. And so that actually will give, well, there's a mirror plane in this material, so that the crystal field is always in plane, so that the spin-orbit field is always out of plane. So that it actually, the spins are locked to the outer plane direction, and SZ is a good quantum number. And so it's basically like an Ising spin system. And the K and K prime point, actually each by itself, it breaks the time reversal symmetry, so that there is in general spin splitting, although they are of opposite signs from K to K prime, because they are time reversal copies of each other. So you get a large spin splitting, in particular in the valence band, that's about half a EV spin splitting. This is spin down, spin up, this is spin up, spin down, because the K and K prime are time reversal copies. Okay, and so this valley spin are locked, so that you actually just get 2 degrees of freedom left, and you have nothing else.
I really need that chocolate, so I was going to ask, the green and the yellow sites, these are both moly or tungsten?
So this is actually the transition matter. These are the 2 chalcogens directly on top of each other.
I see. Okay. Yeah. So that's selenium or whatever.
Yeah.
Yeah.
Sorry, these pictures of the conduction and valence band are to scale, so the gap is much bigger in the valence band and the conduction band? Is it?
Yeah, actually, the spin splitting in the conduction band is pretty small. It's on the order of 30 to 50 millielectron. It's about an order of magnitude smaller.
Is there a simple way of explaining why it's so different?
Oh,
The two bands?
it's actually connected to the d orbitals, which d orbital it is. And now I forget which one is which. One is the dc square, the other is dxy minus dyc.
Right.
Yeah, so it's related to that.
So then the strength of spin orbit coupling happens to be different.
Yeah, yeah.
Thank you.
Okay. Yeah, so like twisted bilayer graphene, you can form Moiré lattice by using two layers of the same material. We call it Homo-bilayers. Then you can twist it, and it gives you a Moiré period. And the Moiré period proportion is actually equal to the lattice constant of the original material divided by angle theta. Yeah, in a small angle limit. There's another way compared to the graphene in this type of material, maybe even simpler in this particular case, is to use a heterobilayer, to use two layers of different materials. For instance, tungsten selenide, tungsten sulfide. Even with a 0-degree twist, there is a lattice mismatch between the two materials, which is about 4% in this particular combination. And so the Moiré period is actually given by A divided by delta. Delta is the lattice mismatch in a small angle limit. So you also can produce a Moiré lattice like this. So you have a combination of using different materials to do it. And you can really see the Moiré lattice. And this is a work in collaboration with Dave Mueller at Cornell. This is a high resolution STEM image of this particular heterobilayer. And the small dots are the real atoms. But on top of that, you also see the formation of a super lattice structure. And I'm just showing the unit cell for this particular case. Okay. So in the heterobilayer, actually things are very simple because the bands from the two layers, they are very far off in energy. And as I told you that in monolayer, because of spin orbit coupling, the degeneracy, the spin degeneracy is removed in each valley, so you only have 2 degrees of freedom left. Okay, so to a very good approximation, if the Moiré length scale is very large compared to the atomic length scale, then to a very good approximation, you can just forget about the original lattice of the material and just treat the electron with the effective band mass moving in a smooth periodic potential given by the Moiré period. Then you just zone fold the band structure from the big Brillouin zone to this mini Brillouin zone. Then you just get a series of flat bands because of the extra Bragg scattering due to the superlattice formation. Okay. And then these bands are actually very simple because they're just two-fold degenerate. So each of these bands is two-fold degenerate. Simple compared to the graphene case. So because of the simplicity, you only have two-fold of the degree of freedom left. And Wu and McDonald actually in this 2018 paper showed that if you just map the low energy physics of the topmost band here, you can actually map the model to a Hubbard model on the triangular lattice with a T term between neighboring sites and the U term that's on for the on-site Coulomb repulsion. Moiré period is about 10 nanometer.
Yeah. Ask to clarify, so what are the main channel degrees of freedom? So you said it's not spin, so after you fold it,
It's actually valley. It's the valley has the SU2 here.
right. The valley sort of coupled with you, right? So you
Yeah, the
K spin up or K prime spin
Yes.
down. Is it in a Hubbard model?
Yeah.
What is the label on the convection levels?
Oh, it's the valley. It's the freedom. Yeah. The spins are actually Ising spins, right? Up and down. So it actually does not have the SU2. But the valley actually in this low in mapping to this low energy model, it actually has the SU2 in the valley degree of freedom. For instance, like an antiferromagnetic state would be an intervalley coherent state, but with a Q vector.
I can sort of see how the copying would be copying within the same valley. That's natural. What's harder to see is the Hubbard chart. It would be like n up times n down. Now it would be n k value times n k prime value. Okay, so is there a reason?
Yeah, you also have, but you also have the intervalley Coulomb, right?
So yeah, so that's what you're saying. That the
Yeah.
U term is basically intervalley Q.
I think it has both intravalley and intervalley.
There's no suppression of the intervalley Coulomb. you can have intervalley Coulomb, you cannot have intervalley Hawking, right? But you can always have intervalley Coulomb.
Yes, I'm not objecting to that. I'm just saying, how would you write intra-value term for the Hubbard one?
E squared over R.
Well, no, I know, but you can't write down U prime times M up square. That just goes to one. So I mean,
I just up and down are just new labels.
Uh-huh.
That's it. The Coulomb integral.
Yeah, that's. Okay. Did he answer your question? Yes. So the T, well, it's the kinetic energy, so it's proportional for the massive band, it's actually proportional to 1 over the Moiré period square. It's about 1 to 10 millivolt. You can, this is a heterobilayer. I'm talking about heterobilayer so far. And U is the onside. It's about this Coulomb form here. It's about 100 millivolt. And U over T is actually proportional to the mass, the band mass times the Moiré period. So the longer the Moiré period, the stronger the interaction in this system. Okay, so heterobilayer Moiré has been demonstrated to be a pretty good mimicking the Hubbard model. For instance, we have observed Mott insulator and Mott transition, the emergence of local moments in the Mott insulator. The Whitman Mott states, or people also call it the generalized Whitman crystal states, spin polarons, etc. But there's no superconductivity for some reason observed in heterobilayer. Maybe the reason is actually that the U over T is really, really huge in this kind of heterobilayer material. And so let me just give you a very simple example of the heterobilayer Moiré, so to try to show that indeed the physics is quite close to a Hubbard model. So we have a device structure look like this. The sample is this heterobilayer Moiré, and we put the sensor next to the sample but not touching it. So there is a very thin hexagonal boron nitride spacer that separates the sample and the sensor. Then we have the additional graphite top and the bottom gates to be able to tune the doping density in the sample, and also keep the sensor to be in charge in neutrality. And what we do with the sensor is that we shoot light onto the sensor, we generate these electron hole pairs, and the electron hole pairs, they form excitons, and then they have Coulomb field lines, which are illustrated by these black lines here, that can penetrate through the sample. And so if the sample is in some metallic state with with high compressibility, a compressible state, then that will screen this field line very well. Then you have a weaker binding energy for the excitons, for the optically excited excitons. And if the sample is in some incompressible state, then it's actually weaker in the screening of this optically excited exciton. Then you expect a larger binding energy for the exciton. So by just measuring the binding energy of this exciton of the sensor that is not touching the sample, you know that whether it's in a compressible state or in compressible state for the sample. Okay, so this is the result we published quite some years ago. That this axis is the gate voltage, which tunes the filling factor or the doping density in the Moiré material. This is the photon energy that we are doing spectroscopy on this sensor layer here, and the shift in the photon energy of all this resonance here, meaning a change in the exciton binding energy, basically. Okay, and these are the labels for all the different filling factors of the states that we can identify in this particular sample here. Negative gate voltage is hole doping, positive gate voltage is electron doping. Filling factor 1 here means a half band filling. Filling factor 2 is full band filling. Okay, and of course, in addition to filling factor 1 and 2, you also can see a bunch of states at fractional fillings. So a filling factor 1, the most natural state is a Mott insulator, and filling factor 2 is a band insulator. And the fractional states, I think now it's also confirmed by STM imaging that it is really a series of Whitman Mott insulators that because of the longer range Coulomb repulsion between the electrons, they self-organize into this states that spontaneously break the translation.
It's not just the Hubbard model. So.
It's actually extended.
Right.
Yeah. So it's not just U, but you also have the V terms. Actually, you need the V terms to be able to stabilize these states. Yeah, and some of the states also break the rotational symmetries as well.
Okay, so you just draw the spins in a particular configuration. So is that experimental or is it's just speculation?
Yeah, so this is let's say that the theoretically expected state, the ground state experiment. So far, people have not been able to really show that it's a 120-degree neo state. When I talk about the Homo-bilayer later on, I think we have some evidence to show that it's an anti-ferromagnetic order state, but we still don't know whether it's in this particular configuration for the states. Okay, well, you may not be happy that maybe, how do you know that it's a Mott insulator? And I think one of the things for the Mott insulator is to actually show that you have local moments, and you know that you have a Mott insulator. And so one way to show experimentally we have local moments to measure the temperature dependence of the magnetic susceptibility. So this is the experimental result for the state at filling factor equal to 1, this particular state here at half band filling.
How do you do that for a single layer?
Well, actually, this is not really a quantitative measurement of the magnetic susceptibility. We are measuring, we are using a magnetic circular dichorism using light to measure basically how much, when you shoot light on the material, you get a phase change for the left and right-handed component.
Why is it that it can be done here but not on bilayer graphene?
Oh, here is that the material has very nice excitonic resonances that can really amplify the signal because of the resonance. And bilayer graphene is optically flat. You know.
Excuse me, you said you have Valley index instead of spin.
Yeah, Valley index when coupled to the outer plane direction of the magnetic field. You cannot couple the in-plane magnetic field. So this is measured under outer plane magnetic field only.
So what is the spin configuration, or is it disordered at that? I guess you're saying it's disordered.
Actually, yeah, we believe it's disordered because you can try to make a fit to Curie-wise behavior, and you get a negative Curie-wise temperature, but it's a very small number. So I think, you know, with additional geometric frustration, I just don't think that we can actually observe a 120-degree neo order in this particular case. So the problem with this heterobilayer is that the U over T is very big. So the local moments are more or less like they are not really talking to each other. It's basically like a paramagnet.
And what's the mechanism of this?
Oh, we are actually just we are doing a magnetic field dependence at each temperature, and we're just fitting the linear slope in the zero magnetic field limit.
So sorry, just to try to understand this of the most basic terms. I know you are not actually doing a static magnetic susceptibility measurement by applying a field and measure magnetization, but in principle, it should be equivalent, right? I could hypothetically apply a field, measure the magnetic moment, divide the two numbers, and then I get my susceptibility. But in your model, the index is the Valley index. So are you saying basically that one of the values of the Valley index is coupled to one value of the set component of the spin? So it's not hybridized or anything, it's just...
Yes.
Okay.
Yes. And one value will couple to a particular spin, and that will respond to, you know, spin up. Then apply magnetic field, you get a Zeeman term for that. You get a Zeeman splitting.
Right.
And what's even nicer in this material is actually that the left-handed line and right-handed line will just also couple to states only in a particular value.
Right. So basically, your magnetization is actually the Valley imbalance.
Yes.
Great.
Which you
Thank
can
you very
access by the light. Yeah.
Thank
Although
you.
not quantitatively, we cannot put like how many ball magnetons there.
Okay, yes, it's proportional.
Yes.
So in this picture, which is quite important, this is a fully Eisen. Okay, now how should I then understand the 120 order then PSR?
It's actually a phase coherent state, really. It's just that the two values, they spontaneous form phase coherent, but the phase is actually modulating with this 120 degree.
So
in the lattice scale.
it's still the next one.
Yeah.
But sorry, you said you don't have any order. Or
Well,
you
we don't have any experimental evidence in this particular case that there's a new order. But I will show some results that we probably have some evidence for anti-ferromagnetic order, you know, in the other system that we studied. Yeah, I mean, this particular case that the J is really small, you know, in the Hubbard model, T square over U, the U is very big in this particular case.
So when you draw these pictures of 120°, you don't really have that. There's no.
Actually, I'm not even
Pi.
drawing 120°.
You did on the previous page.
Yeah, that was, yeah. This was, wait. Yeah, this is actually 120.
Based on this measurement, you don't have the 120°.
Well, yeah, actually, I don't think we have, because our temperature, the lowest temperature in our measurement is above this temperature. So it's just like a parameter.
And you see some deviation perhaps, right?
Yeah, you actually have a little bit of
That's very
deviation.
good.
Yeah. In fact, the high temperature part agrees really well, but then the low temperature has a little bit deviation already.
Is it possible that you have a phase transition of 4 degrees based on that?
It's down to two,
I
right?
think you really need to imagine that.
And what if the potential for cooling is to lower temperatures?
You know, it's an optical experiment. We shoot very little light on it in doing this experiment, but I wouldn't say we can go to 50 milli-K. Probably be somewhere between 100 to 200 milli-K is possible. Yeah. Okay, so that's all about heterobilayer. Now I switch gear to Homo-bilayer. Actually, why doing Homo-bilayer is that it just gives you an extra knob to tune the U over W or U over T ratio, because the Moiré period now is inversely proportional to the twist angle in small angle range. So we can actually just change twist angle in our devices to try to, you know, lower this value to you know, just to basically increase some of these energy scales, like the exchange energy scale system. So a few words about twisted Homo-bilayer. It's actually a little different compared to the heterobilayer case. This is the structure. Actually, the first experiment was done on Homo-bilayer was done by Corridine and the Fai Mak group. And so the way to understand the band structure of the Homo-bilayer is that you have a top layer Brillouin zone, bottom layer Brillouin zone. They are at just angle theta. Then the two Brillouin zone define a mini Brillouin zone like this. And you can calculate the band structure in a continuum model. And this is the topmost valence band in this twisted tungsten selenide in this case. And a simple way to sort of understand this is actually that you have the layer number 1 band here centered at K, which is this point here. And then the layer number 2 electronic state centered at K prime here. And when they cross to each other, then you have a band opening. You have a level repulsion, and that actually gives rise to a Van Hoos singularity at this particular point, at the end point of the Brillouin zone. So that's one way to understand the formation of flat bands in this material. And that's under zero electric field. You can actually apply a perpendicular electric field to the material, and then you will put the two layers at different electrostatic potential. And it turns out that in this case, the vertical electric field can act as an effective spin-orbit term that's tunable by the electric field in these Moiré bands. And how does it work is actually, so this is the calculated band structure under a finite displacement field. And you can actually now see that besides the gamma point and the end point, you actually now have a spin splitting in the bands generated by the electric field. And the way to understand this is actually the following. You have a layer 1 band, you have a layer 2 band, but now they are at different potential because of the electric field. And so this is from one of the valleys. And of course, you have the other valleys, which will basically do that. And so when you combine everything, that's how you actually get this spin splitting generated by the electric field. So the electric field term here actually acts like a tuning knob for the spin-orbit interaction in the band structure of this system. So people have mapped the low energy physics of this particular band, including the electric field. So it's actually a modified triangular lattice Hubbard model. We have a T term, we have a U term, but now there is also this phi term here due to this electric field tuned spin-orbit interaction. And once you put on a finite electric field, you can think that the electrons, when they hop on the triangular lattice, they pick up a phase of phi that gives rise to a spin-orbit splitting in the bands at finite momentum.
So is it a DFT calculation or is that something?
It's actually a continuum model. And the parameters is from the DFT. The parameters is from the DFT. But these flat bands here are from the continuum model.
So how different is the gift?
So how they do it, how people now, if I understand correctly, how people these days do it is to calculate really the DFT Moiré band structure at larger twist angle that the unit cell is not that big. And then they fit the continuum model to the DFT bands to obtain the continuum model parameter. And then they use the same set of continuum model parameters to calculate bands at different twist angles.
To the same twist angle, you cannot do the DFTs.
Very small twist angle is very hard because the unit cell is very big.
It's quite hard to relax this much.
Yeah.
But
And
people do this local stacking approximation as well.
yeah. But let's say that this approach is also an approximation. You calculate a larger twist angle, you assume that the parameters don't change with twist angle, but that's not really the case. So we are, but what I'm going to tell you is actually that we are limiting ourselves to pretty large twist angle devices. So the lattice relaxation is less important.
So you're the one, oh,
Are you saying that for Phis have different signs on different ports?
Yeah, so one value when they hop with they pick up a phase of phi in the bracket. And the other value will pick up a minus phi.
yeah, I'd like to clarify the layer, sorry, the layer versus the valley. If I look here, there's a K and K prime.
So
So it's the reason that the layer one is, if the top of the band is a K, there's a layer K.
oh, it's actually it's from here. So they are actually both in K
Oh,
from the big value.
That's right, it's a K.
But they are now in the K and K prime. Maybe I should call this maybe a better neighborhood is that this is kappa and kappa prime
Yes.
of the resemblance zone. But this is actually the K and the K of the of two layers.
I see.
Yeah.
And the other question, the twisted ballet graph.
Yeah.
Sort of natural to think about K and K for kappa and kappa prime points, because that's how you kind of your outcome bands.
Yeah.
And that's what sort of your argument, that's the most interesting physics comes from.
Yeah.
Having the logical facts as well. Here though, if I look at your bands, there's nothing special about.
Yes, because there's no direct point to even
Exactly.
begin with in the monolayer material.
That's right. So
Yeah.
is there a conceptually big difference between these Homo-bilayers and twisted bilayer graphene?
I think that there is a big difference in the in two cases. For instance, in the twisted bilayer graphene, the single particle bands, you do have direct points, right? At the kappa and kappa prime, but you don't have.
Topology.
And you also have, you almost cannot avoid topology in the twisted bilayer graphene. But in this case, you actually can have bands without topology at all. Okay, so yeah, so there's this extra term which is different from the more conventional Hubbard model. But this term is tunable by the electric field, actually by a large number, but from 0 to pi/3 or something like that. So that's the electric field can effectively tune this
Tiny question. Tiny question. This is not even worth a chocolate. Just confirm that you've used the label sigma equals plus minus in Hamiltonian in the first term, but then in the interaction term you have up and down. But that's just labeling, right? It's the same label.
Yeah, yes.
Just
Yeah.
thank you.
Okay, so that's but now let's just consider. So that's a Hubbard model. That's a Hubbard model. But now you can actually take the large U-over-T limit at half band filling, then you can map the Hamiltonian to a spin Hamiltonian. It turns out that once you do that, you actually have two terms in the spin Hamiltonian. One is the XXZ model, the other is the BM interaction term here. If you don't put any displacement field in the system, meaning no vertical electric field applied to the material, then phi is equal to 0. And in this case, you just recover the triangular lattice Heisenberg model. and maybe the potential ground state has been liquid if you have a weak Mott insulator. But if you put a large displacement field, actually in our material, we do put a large displacement field, and the phi is on the order of pi over 6. And then the anisotropy for the spin Hamiltonian is actually important in that case. And theoretically, people have predicted that the 120-degree New order under a large displacement field is the more natural ground state. Without electric field, it's possibly a spin liquid, but with displacement field, most likely it's a 120-degree New order that I'm going to show some results later. So Homo-bilayer Moiré is also a very good model system to mimic the Hubbard model. And in addition to all these phenomena that have been observed in the heterobilayer, people also recently observed superconductivity. So that's the remaining part of my talk. All right. So a typical device that we study is a dual-gated sample. You have the Moiré sample. In this case, it's twisted tungsten selenide, and you have the top and the bottom gates, so that you can experimentally you can tune two parameters. One is the vertical electric field that tunes the spin-orbit coupling in the Hamiltonian. The other is the density, basically the doping density in the material. So you can independently tune these two parameters in a typical experiment. So this is a map. First, I'm going to talk about a larger twist angle sample, first done in Colombia. It has a small U over W ratio here. And this is the map of the resistance or the resistivity that they have measured as a function of these two parameters. And on the right-hand side, I'm showing a phase diagram that's just reproduced from a single particle band structure calculation, displacement field and filling factor here. Again, filling factor 1 is half band filling. And you can actually see two distinct regions. One is the layer polarized region that typically happens as small density and high electric field. And that's very natural because you have a high electric field applied to a small density, you basically polarize all your holes to one of the layers only. So in this case, then the physics is very similar to just a monolayer physics. So there's very little Moiré effect in this region here. Everything is pretty much like a monolayer material. So that's not very interesting in this regime. So the more interesting regime is inside here in the small electric field region, and typically at higher density, that you get this really the charge, the holes shared between the two layers. We call it the layer hybridized region here, and you get all this Moiré effect. And this dashed line is the dispersion of the Van Hool singularity in the band structure. You tune the electric field, you change the location of the Van Hool singularity, and you can actually see the Van Hool singularity in experiment. I hope the color is sort of clear enough that there is a local maximum of the resistivity here. That's actually the Van Hool singularity here. And these boundaries are the layer polarized, the layer hybridized boundaries. So in general, it works really well that there's a single particle band structure. Compare the experimental data to the theory, it works really, really well. And then now you also see there is this little region here that when the Van Hool singularity cuts near filling factor equal to 1, cuts near half band filling, you get a small resistance state. If you zoom in, it actually has zero resistance. And TC is about 400 milli-K. And the claim is actually that this superconducting state in their paper is that is next to an antiferromagnetic metal, which is this state here has a larger resistivity.
But why are you getting a maximum resistivity in the Van Hoff singularity? You have a divergent density of state, resistivity should go down.
Now, if you think in terms of like, so I can think of two effects. One is that if you have a Van Hool singularity, it's like the effective mass is larger. And the other is that the scattering rate most likely will also increase when you have a larger density of states. Yeah, that's my way of thinking about it. So it's basically this, the mobility will just increase. You have shorter scattering time and a larger effective mass via the Van Hool singularity.
So this is not a real resistivity measurement.
This is real resistivity measurement.
4 point?
Yeah, 4-term and 4 resistivity measurement. And so that's the claim that this metallic state with a larger resistivity is an antiferromagnetic state. And there are also theory papers that claim that is pretty well described by recoupling theory. in this large disangle sample with a small U over W. And
They measure the magnets.
not really, yeah. So it's they measure some Hall effect, and I think we will also show some Hall effect data that it suggests that there is a reconstructed Fermi surface here. So that's
Can you measure susceptibility in these systems?
yeah. So I'm going to also show you the results. Yeah. So a different experiment is from our group. We look at a smaller disangle sample, and in this particular case, it has a larger U over W ratio. Now you can actually compare the phase diagram. Again, this is vertical displacement field and the filling factor here. You also can see the layer polarized region. These are large electric field domain, and then the layer hybridized region here. But you can also see that compared to the large disangle sample, we have a strong insulating state. This is a log scale. Okay. We have a strong insulating state with a divergent resistivity in most of the regions at filling factor equal to 1, meaning at half band filling, you have a strong insulating state here. So the band theory actually does not work near filling 1 in this case. And the superconductivity, which this state here appears exactly near half band filling and just come out of the Mott insulator. So you can zoom in. The superconducting state appears only very close to a half band filling, and it just comes out of the Mott insulator tuned by the electric field. So there is a direct electric field tuned superconductor to insulator transition, but this is not really due to disorder, but it's really intrinsically tuning the band structure effect.
Okay, what does the field tune? Is this angle farming? Is there some intuitive thing? Does it tune the bandwidths? What does
Which field? Sorry, the electric field.
Yes.
The electric field mostly does not tune the T. It mostly really just tunes the location of the Van Hook singularity, which is that phi term in the spin orbit coupling. But in this particular case here, the Van Hook singularity is actually very far from the filling 1. So we still don't know why exactly at this very small electric field region is such a strong sensitivity of the state to a small electric field.
Well, I think it actually includes zero electric field as well. So
Yes.
this would be just a pure Hubbard model, right?
Actually, this would be a pure Heisenberg.
Pure Heisenberg.
Yeah, with the strong large U over T limit, this would be a pure Heisenberg model. But it's basically at this point, it's just that the bands do not have any spin splitting. Yeah, it's pretty close to the triangular lattice hub, the conventional triangular lattice Hubbard model. Okay,
And it is a superconductor.
it is a superconductor, yeah.
Isn't that amazing? Well, amazing. Yeah.
So let me just put a short summary of this two limit of a large twist angle and a small twist angle. One corresponds to small U over W, the other is large U over W. And the large twist angle superconductivity is going to yeah.
The conventional wisdom that it's 120 degree anti-Fai Mak, right?
Well, actually, it's I would say that if you look at here, quite likely a high electric field, it is 120 degree. But at a low electric field, you really have a two-dimensional Heisenberg model,
Right,
and I think that should not order. Right.
120 degree.
No, I think the 2D
Well, no
Heisenberg
longer.
model is expected to have more every order.
Yes,
Wait, even for
spin 1/2, yeah.
high, totally Heisenberg model without
Yeah,
any
totally
so-
Heisenberg.
yeah, the fluctuations are not enough to kill the order.
with this moment witness.
Zero temperature, it's quite okay.
Oh, you're talking about really that the
ground
zero
state,
temperature.
yes.
Mhm. Yeah, there's no finite temperature long range order, but there is a zero.
Yeah, but it would have a very, very long correlation then with
Uh-huh.
ground temperatures.
Yeah, that is possible. Yeah.
But here you're seeing it's the superconductor.
Oh, but yeah. Okay, I'm going to show you some more results, and probably it will be clearer as we go on. This actually I call it large U over W, but it's not that large. If you decrease the twist angle further, this entire thing is just a Mott insulator. You don't have the superconductor.
And how strong is the evidence with the superconductor? Can you show your your nice resistivity curve?
Yeah, well, actually, maybe it's better to show. So this is another case here. Yeah. Yeah. Oh, and maybe I have it. Let me just.
The different curves are different magnetic fields.
Yeah, there's a different magnetic field, and you can also measure. The the supercurrents as a function of temperature, supercurrent is a function of magnetic field, and these are the supercurrent curves. Yeah, I think.
That's pretty good.
Yeah, and we are pretty confident that it's a superconductor. Yeah. Let me just go back to.
The lattice of 250 millikelvin. How does it compare to the bandwidth in the model?
Compared to the bandwidth, it's more like a compared to the Fermi temperature, right? It's about 10%, few to 10%.
Sorry,
A few percent to 10%
of the bandwidth.
of the TF. TC over TF is you can take about 5%.
What was TF? Sorry.
TF, okay, TF is on the order of few K to 10K, and then you have about 300 milli-K.
But you also have long range Coulomb interaction, right?
Yes, this we do have a longer range Coulomb interaction, and you can actually see its effect because you have these fractional states. That's other, no.
So it's not quite the.
It's not exactly the U Hubbard model again. It's the gate screen Coulomb. We have the metallic gates here. It's the gate screen Coulomb. But if you can try to really mimic the Hubbard model, if you put the gate really close to the sample, that let's say that it's even shorter than the Moiré period, the sample gate distance, then it's pretty close to just the U.
And what happens with superconductivity?
Oh, we unfortunately we haven't done it because doing that additional distance dependence measurements takes a long time. We haven't done it. Yeah, so I think maybe I just move on. So the next thing we want to do is to really just change the twist angle to hope to achieve some intermediate U/W ratio, and then just ask ourselves, can we get a high TC phase diagram in this theory? So this is a map of the resistivity as a function of electric field and doping density at different twist angles, all the way from 2.7 degree to 4.9 degree. Okay. At 4.9 degree, there is very little correlation effect, and you can see the Van Hook singularity here. You can see the layer polarized state and the layer polarized regime of the phase diagram. And everything just looks like the band structure works really well for this large twist angle regime. And for the small twist angle regime, of course, you have lots of correlated insulators. You have the nu-1 half band filling correlated insulator occupying the entire region of the electric field. You also have the fractional states. But as you increase the twist angle, you actually can see that the zero electric field correlated insulator filling 1 starts to weaken. And then it becomes a metal. Actually, when you cool down further, it becomes a superconductor, and then gets further weakened until finally at this angle around here, the correlated insulator is nearly gone, except that when the Van Hook singularity cuts through filling 1, then you can actually stabilize the correlated insulator in this case. So most of the regime, you don't get a correlated insulator, except that when the Van Hook singularity cuts through it, that's the filling 1. So that's the regime that we want to look at. I think this is pretty close to an angle-tuned Mott transition, that the states go from you barely have a Mott insulator to no Mott insulator if you further increase the twist angle. So we just fix at this particular twist angle, and cool down further, you actually can see superconductivity. It's actually wrapping around a correlated insulator at the half band filling. Okay, and if you zoom in, you have a correlated insulator filling factor equal to 1, and you have the superconducting state wrapping around it. And outside, when you dope really far outside, it's actually a very good Fermi liquid. And you also can see some regions, the whitest region with a larger resistivity, And that's actually, I'm going to convince you that they have a small Fermi surface. These are the doped Mott. These are the doped Mott states.
Question, you said very good Fermi liquid, is that just from the T squared?
Yes, from the T-square diamonds, yeah. And yeah, I already showed this. You can park at a particular point. You can check some basic characteristic of the superconductor. You can extract a coherence length about 34 nanometer. The lattice scale is about 4.1 nanometer. So this is a factor of 8 of the lattice scale. So it's quite tightly bound. And the mean free path of the material you can estimate from the normal phase resistivity. It's about 400 nanometer. It's a factor of 10 or more compared to the coherence length. So it's a very clean superconductor as well. So then let's actually cut at the particular electric field, and we scan the doping and scan the temperature and see what we get here. And of course, we can also change the electric field that I'm going to tell you next. But let's just focus on one electric field. So the band structure is fixed, at least from the single particle point of view. Then we just change temperature. So this is the result. Filling factor, temperature, the map is the resistivity. This is left-hand side, and the right-hand side is the Hall resistivity that we measure under a small magnetic field, but large enough to kill the superconductivity. Okay, so you see that there is a correlated insulator developed below about 3 Kelvin or 3.5 Kelvin. You develop this correlated insulator. And then around the correlated insulator, you also see 2 metallic states that has larger resistivity compared to the surrounding region. And these are traced by the dashed line. These 2 dot Mott insulating states only occur after the insulator actually develops below that 3 Kelvin temperature. And from the Hall resistivity, you actually can see that this is really a small electron Fermi surface pocket, and this is a small hole Fermi surface pocket on the immediately left and right hand side of the correlated insulator. And then you have a sudden Hall number jump when you go beyond some critical doping that I will tell you a bit more later on. Then once you kill these doped Mott insulating state, you get the superconducting states coming out.
Smaller is the field for the Hall than the critical field. Kill the superconductivity.
The critical field is about 150 millitesla at the base temperature. Yeah, it's a few times bigger. We can do this map at as long as we do this map about 0.2 Tesla, they just look the same, more or less. So let me just tell you, walk you through this phase diagram a little bit more carefully. Let's look at filling factor 1 first. So instead of showing the contour, now I'm showing a line cut of the resistivity as a function of temperature. You can see that below 4K, the system becomes an insulator with several orders of magnitude increase in the resistivity. So theoretically, people tell us that this should be 120-degree Neal order, but do we have any evidence for that? So we use the same trick. You know, we measure the magnetic circular dichroism and try to extract the susceptibility, and that's what we get. Magnetic susceptibility as a function of temperature. High temperature part, you get the Curie-Weiss law. You can do a fitting, and you can get a negative Curie-Weiss temperature that suggests the local moments are actually interacting with each other with an antiferromagnetic interaction. But there is a kink. This we assigned it as a Neal temperature. That below this kink you have a suppressed susceptibility system.
Question, you have AU there. You can get your temperatures. Can you in any way extract an effective moment?
Yeah, so that's actually sort of the discussion we had a little bit.
I apologize.
Yeah, and the way we measure this is to measure the magnetic circular dichroism. It's not a quantitative way of measuring, so we cannot extract
no effective moment.
Yeah, no effective moments. But you can get the energy scale from
Sure,
this.
of course.
Yeah, so I hope that we still cannot prove that it's 120 degree because we cannot do the neutron scattering. But I hope that it shows some evidence that indeed it's really an antiferromagnetic insulator and it's ordered.
Do you have an estimate for the exchange in this case?
Basically, this Curie-Weiss temperature is a measure of the overall exchange energy scale between the local moments, and it's basically nearly the same as this temperature here, which is about 7 to 8 Kelvin.
But it's very frustrating, so you imagine the exchange is quite large.
Sorry, Kingston.
The frustration ratio is quite large for this model, right? It's 123 ordered.
Yeah, but the problem is that the Curie wise fitting is that it depends on the range of the temperature you do the fitting. So the Curie wise temperature is also, strictly speaking, is also a function of the temperature range that you do the fits, right? And people actually have studied that in the Hubbard model, that you can do a variable range in the temperature to do the Curie wise fitting, captures and different energy scale. So I cannot say whether that's much larger than the ordering temperature.
I want to have asked it earlier, but you know how in the first part of the talk, when you talked about the hetero-bilayers, you explained nicely how the valleys are coupled to spins and the spins are rising. In this Homo-bilayers, is that also true? And if so, what do you mean by complementary order? Are the spins not rising?
Oh, yeah, the spin is still icing. It's actually still true. Everything is still true there in the Homo-bilayer and the hetero-bilayer. It's just that it's an intervalley coherent order again. But we only, the valley only responds to an outer plane magnetic field, so we only can measure under outer plane magnetic field. I don't believe that it actually has any.
It's Heisenberg pseudo spin and it's Ising real spin. So what do you think about it?
It's not even a Heisenberg pseudo spin, I think, under a finite electric field.
Yeah, okay,
Yeah.
fine.
Yeah. But it has more or less a XY. Yeah.
So I count.
Yeah.
Okay.
Yes. Okay. So by the way, actually, these two are the different samples. One for transport, one for measuring this. That's why the temperature scale is a little different. We try to target nearly the same twist angle, but twist angle is slightly different. These two measurements. So I hope to convince you that we do have some evidence that this is a antiferromagnetic ordered insulator. So we call it an antiferromagnetic insulator. And now just let me walk you through with the remaining time quickly when we scan around the Mott insulator and see what we get. If you dope really far away from the Mott insulator, like more than 10% doping, you get a T-square dependence for the resistivity, typical of a fermi liquid with a small residual resistivity. And we define the coherent temperature scale sort of arbitrarily that when the data deviates from this fitting curve by 10%, we define it as a T-coherent temperature scale, as a crossover temperature scale. And the temperature scale basically goes towards zero as you move closer to the Mott insulator. And you can do the exercise on the other side, it also goes to zero. Yeah.
It's always nicer to show a T-square plot if you want to show a T-square. Just a hint from the heavy fermion community.
Okay.
Always, if we want to emphasize it's T-square, because no one can gauge square by height.
Okay, yeah.
Rho versus T-square, that would be more convincing for us.
Okay,
Wanna
yeah.
convince us.
I'll show you, yeah, but I cannot show you immediately. So things get a little bit more interesting if you dope a little closer to in the underdoped regime. You go to closer to the Mott at the antiferromagnetic insulator. You do a temperature dependence cut at this particular dope. The red curve is the Hall number or the Hall density. It's actually the Hall density normalized by the Moiré density. And the blue curve is the resistivity. You actually can see that below some temperature scale, we label it as the T-neo. The Hall density actually jump. It actually goes from a large Fermi surface to a very small Fermi surface when you go to the low temperature phase. And actually, the Hall density is nearly exactly the same as the doping density that you count from doping equal to 1. So for instance, this is a 1.024 that the Hall density is really like 4% of Hall density. That's really consistent with just doping from the Mott insulator. Okay. So it shows that it has a small Fermi surface. And this temperature scale, again, actually goes down on both sides near the Mott insulator. Actually, I mean, you don't even need you can almost see by eye that this temperature scale actually just goes down on both sides. And then once you get this killed, you get the superconducting domes coming out.
Is the change of the Hall, the temperature where the Hall changes, does it track exactly the temperature, the neo temperature?
Yes. That's actually the previous Hall map here. right? This is actually a large Hall effect will be a small Hall number. This is a Hall resistivity. It's a large Hall resistivity, so it's a small Hall number here. So it really just traces
So
this.
it's just band-folding in some way,
It's actually really like you can think of it that
just tied to the magnet.
once this insulated developed, even I dope a little bit away from that, this gap survives, so that my doping is really counting just from filling one. Right, I think that's a correct statement.
Well, my statement was more than, is it just tied to the antiferromagnet? And it seems like yes.
Yes.
And it's further under focus, right? It's just a band folding. The antiferromagnet has a different Hall number. That's what we try to do everything to sort of pull that out. In the picture where we say a strange metal has the Hall reconstruction that is not just coming from order. It's from localization, delocalization of a charge that has nothing to do with order. But here you confirm that it is the order that does it. Right?
Yeah, so this part is ordered. Yeah, this part is ordered, but you can get rid of the order by doping.
No, I see that, but the Hall changes because the antiferromagnetism is. It's related, right?
So it's so maybe I can just say that it's not a just √3 by √3 reconstruction of the Fermi surface, because this is really that you have an insulator here. If it's a √3 by √3, you still have a very large Hall number, but here we have a very tiny Hall number. You know, the Hall number is just coming from the doping away from filling one. It's not, you know, it's not just a simple √3 by √3 that you have a large Fermi surface, then you √3 by √3 and get that. Then you know you will be jumping from somewhere down to here, for instance.
Okay, so it's the antiferromagnetism and the Mott insulator transition that all have a different.
Yes, you know, you have a, it's really like a filling one, we have an antiferromagnetic insulator, but you dope a little bit away from it. The Hall number is actually, you have to count from filling one. It's very different from, you know, √3 by √3 of the band density. And actually, I mean, you can do on this side also, the Hall density is also really small electron density on this side. It's again, really just, you count the doping from filling one.
If it's X and not 1 minus X.
Yes, yeah, you know, the band density will be 1 plus X or 1 minus X here, but it's X, the density is X. Then you can cut at you know, the dome of the superconductor. You get a superconducting transition about 300 mK, and then you just get a strange metal with the T-linear resistivity spanning actually about 2 orders of magnitude in temperature down to the lowest temperature that we measure. And the strange metal also has very small residual resistivity, so it's a clean strange metal.
How high does the linear resistivity go up to?
We actually haven't measured to more than 20.
Yeah, I see.
Yeah,
So more than 20. So
most likely it will just keep going, but I don't know where it is. We don't know.
Well, at this point, you're above the coherent temperature. The coherence is Fermi liquid, so is your strange metal a Fermi gas?
Yeah, actually, so at a high temperature, you can still say like maybe that's more trivial because eventually this guy here, but that's around this doping here. So at very high temperature, it actually will be T-linear anyway.
Right. So is your conclusion that strange metal is the same as Fermi gas? Because you're getting your linear resistance basically going above your coherence temperature.
Well, basically,
coherence temperature
it's just that you get this T-linear behavior all the way down to the lowest temperature that you can measure.
Right, because you have no coherence.
At this point, then you just lost.
data that makes it clear that's not true.
Okay.
Yeah. But we'll never get to it because there'll be so many things.
But let me also show you the other side.
Sure,
You know,
sure.
yeah. Then you know you can just ask more questions later on, and you can also cut on this side. But this side you also get a T-linear at high temperature, but there is a T star temperature scale that below that it deviates from the T-linear, and I think P has always asked me whether the Hall angle is T square dependence. The Hall angle is T square dependence. The red curve is the Hall angle. And one can try to extract how the T star depend on doping we define the T star as 10% deviation of the experimental data from this high temperature linear fit. And that's how the T star would look like. Okay. And once you cut the point here, when the T star and the Fermi liquid coherence temperature both vanish, and you really get a strange metal in this case, all the way from 50 milli-K to 20K in this case. You don't have any superconductivity in this region, so it would just be totally T linear with the T square Hall angle. Also,
So the T square Hall angle.
20 Kelvin?
Yes, actually, this is plotting. This is not plotting. Yeah, okay, I'm plotting only to 10, but yeah, it will extend to about 20. Wow, beyond 20, we don't know.
And what's the temperature dependence below T star? It deviates from linear, but what does it become?
It's
You showed it on
it's
previous-
like this.
Yeah.
I don't know. It's really like a.
You haven't fitted it to anything like a square root or
It
something?
looks like a sublinear, but yeah, but we didn't try to fit to anything. Yeah, we didn't try to fit to.
Looks a bit like a square root.
But in this particular cut, there's superconductivity, so I don't want to say. But in some other cuts, there's no superconductivity. Then, yeah, it's sublinear. Yeah. So I'll skip that. And so, well, I also skip that. So we construct the phase diagram of this particular measurement. So we start with the antiferromagnetic insulator. You dope away from it. It has a small Fermi surface X rather than 1 minus X or 1 plus X. Then when you kill those two states, you get the superconducting dome. When you dope far away, you have the Fermi liquid. You also get this some additional T star temperature scale that we don't know what that means. And at the bottom, I'm showing the red curve at the Hall density. And the Hall density actually jumps by 1. The Hall number jumps by 1 near the superconducting dome. Okay, so you get a small Fermi surface around 1. Then it jumps by 1 when you go away from the superconducting state.
That's your T0 statement.
That is the T equal to 0 statement.
That was exactly my question. So it is right at the optimum dome.
It's yeah, actually, it's very close to optimal doping. Yeah. Well, yeah. So it looks actually like the cuprates. And so let me just walk you through very quickly. We can cut a different electric fields in this particular case. Then the electric field tunes the band structure. So let me just present a few cuts quickly, then I'll wrap up. Is that okay? I have.
That's great. You've got 10 more minutes, although.
Okay, then I just wrap up with just
Yeah, if
showing
you want to
you-
have questions, it's better if you take 5 minutes.
Yeah, so I will do it for 5 minutes. So you can first you just move a little bit closer to this insulator to superconductor transition. Then this is the phase diagram. The antiferromagnetic insulator gets weaker. You see that the ordering temperature goes smaller, and then the range of the doped Mott insulating state with the small Fermi surface also shrink like this, and the superconducting TC actually goes up when you get closer to this point here. Okay. And this is the phase diagram, but it actually looks very similar to the phase diagram I just showed you. And again, there is also a Hall density jump that's pretty much pinned to the optimal doping. The Hall density jump is by 1. And when you move even closer to the superconductor to insulator transition, but the electric field then gets further weaker. And now we don't really see any sign of a dope Mott insulating state, because once you dope from the insulator, you immediately get the superconducting state. And but the phase diagram still remains similar. And finally, you move out of the insulator, you just get one superconducting dome left here, and you just get the Fermi liquid far away from this dome. But when you are talking about in the immediate vicinity of this dome, this entire range of the doping density, you actually do get a strange metal that I will show you some more data. And at these optimal doping here, actually now you don't have the insulating state. The Hall density jump is by 2, not by 1 here. So it's really that that's what you would expect when you move away like from a Van Hook singularity. Remember that we are actually pretty close to a Van Hook singularity. So this is returning everything back to the band picture that you just jumped by 2.
And TC has gone up, right?
Huh?
Compared-
TC
has
keeps
gone
going up, so this is a plot of optimal TC This is the critical electric field for the superconductor to insulator transition. The ultimate DC keeps going up, the Tn keeps going down, then the ratio, gets about 20%. But the ratio may not mean too much anyway, because you can go to infinite when you don't have any insulating states. So this is the last slide, and I'm done. So the strange metal, actually, whether it's a critical point or a phase that covers a range of doping density, seems to be dependent on the electric field. This particular electric field, which looks like basically a phase diagram that look like this, you can actually say that it's more or less like a point, that the T-linear resistivity only occurs in a very narrow window of doping density. When you dope a little bit away from it, it deviates from the T-linear behavior. On the other hand, if you tune to an electric field that more looks like this here, then you actually do have a range of density that goes from, for instance, from about 0.85 all the way to 1.01 here, pretty much over this entire range here. That is pretty much just T-linear down to the lowest temperature. And only when you go away that range, then you get a deviation from the T-linear resistivity. So I think whether it's a phase or like a critical point, it really depends on the tuning parameter in the electric field, which tunes the band structure. Okay, so
Look at the lowest temperatures. Where are you making this? Where are the values that you think it's all linear? The lowest temp-
yeah, for instance, this is 10K to about 50 milli-K.
Yeah, but look, just the curve above it actually.
Oh, it's a superconducting state. Oh, these curves are vertically upshifted. So this is the yeah, this is a superconducting transition. This is a superconducting transition. Then once you go away from the dome, you more or less recover this.
Do you think the deviation at low temperature is not significant? I mean, look at your scales, right? You should really zoom on below 2 Kelvin. That's why the phase diagram.
Well, I mean, this is a superconducting. Well, maybe if you this deviation, I wouldn't say it's insignificant because it's a superconducting state. Maybe the best way to do it is to apply a small magnetic field to the superconductor, and then but we didn't do that at this point. But this is at least above TC for these two curves.
You are probably already in your disorder review. It's not entirely everything the same across your sample, right? I mean, there will be some disorder and then this small change of something.
Hey, but just look at the data.
Yeah, but these two are still good, right?
Sorry.
These two are still good. You don't have the superconducting state, right? These two curves still very much T-linear. We already moved out of the dome already in this case, right? So I'm talking about maybe around here and around here, that we don't have the superconductivity anymore. Still very good T-linear.
If I can get the gist of what Zulika is pushing on, I think she would like to attribute the phase to a state of greater disorder.
Of course it is. Yeah.
That's what
Well,
I'm picking up. But I don't think
Rule it out.
that's not consistent with the data.
Why
Wait,
would you
what
say so?
disorder? Sorry.
No. I mean, the question is it really meaning intrinsically there will be a strange metal phase? Or does it?
So our strange metal.
Go in your level where everything is due to this.
So let maybe one thing we can comment about the disorder. So for all of the strange, actually I can pull out some additional data to show you. So the residual resistivity is 50 ohm or something. It's very small compared to H over E squared. So
It's a luxury. In heavy ferments, it's 50 milliohm. So it's huge.
Wait. This is a sheet conductivity. This is sheet resistance. Two-dimensional. This is two-dimensional conductivity. At least a mean free path would, for this case, would be about half a micron. Something if you use the KFL to estimate. Actually, what else do I want to say? Another thing to check whether it's really due to the disorder is that you can make a plot of the density dependence of this slope, and also the density dependence of the residual resistivity here. And there's no correlation for that.
Wonderful.
Yeah. So the slope is nearly unchanged, but the residual resistivity can change by an order of magnitude.
Between what and what, sorry.
When you change the doping density, the residual resistivity can change by an order of magnitude, for instance, but the slope is only changed by 20%. And they have actually totally different doping dependence. I can pull out data to show you.
For the narrow range around that we were showing, it changes the residual resistivity changes in order of one.
Yeah, you over this range, for instance, the slope doesn't change almost, but the residual resistivity change. Yeah. Well, you can sort of see that the kind of heat mark maybe not so clear.
You're,
This is a lot
you're,
wrong.
you're tuning your filling by gating, right?
By gating.
Why would residual resistivity vary with gating? I think of it as scattering off of defects, off of, various things. So the fact that residual resistivity changes, I don't understand the mechanism for that.
Well, the density changes and
Any squared tau over n could change.
well, and also
Absolute terms, n doesn't change very much.
and also now it's actually
And residual resistivity doesn't necessarily follow.
and
N
here
can also change.
here is very close to the Van Hool singularity. Here is very close to the Van Hool singularity. So when you change the doping, you sweep through the Van Hool singularity.
Pseudo gap somewhere.
Can we let guys finish the talk and then we go to questions?
I'm done actually. Yeah.
Okay.
Yeah.
I'm done.
Okay, let's we're out of time, but we're gonna have questions anyway. Yeah, good.
Yeah, so it's about the pseudo gap. So you have the anti-ferromagnets. What about the pseudo gap? How would you define it?
Well, probably just the pseudo gap thing is actually very close to the. So we think probably the T star is the pseudo gap because in the cuprates actually there's also something pretty similar. But we don't have more to say about whether there is a really pseudo gap phase around here. We don't have more to say at this point, unless we actually find something that we show that there is some kind of a gap or something.
Another question about energy scale. So the critical temperature of superconducting, put it into units of T and U and so on, what fraction of T with
I think so this is a bit like the ordering temperature is on the order of J, let's say. This is about 10-20% of that. Yeah. And you can also try to estimate use the doping density away from one, what is the Fermi temperature of that, and the Tc over Tf 10 to 20%, so 10%.
Alex.
Thanks, beautiful talk. Did you see any signatures of charge density where they are in place now?
No, we have not done any of those measurements, but maybe actually there's a possibility of stripe phases. The states break the rotational symmetry. I think it's possible that we can do. Actually, we can do again use our optics to do the linear birefringence measurement to see whether there's spontaneous rotation symmetry breaking in something, but we haven't done it yet.
Yes, Victor.
I have to follow up on this slope of the linear staying constant in spite of the zero changing drastically. That's the content to it. So in the cuprates, when Pierre says it's convex, it means because he does it in the cuprates, but there, the only reason when it works is that the carrier concentration doesn't change a single bit because they take the exact same sample and irradiate. Then the only thing that changes is the defect concentration. It's really the defect scattering that changes. That's when the zero changes, and the slope of the A prime, the slope of the linear resistivity doesn't change. So in your case, you want to include the carrier concentration for that. That enters also in the slope
Let's see
of
his
the linear
data.
resistivity.
Yeah, let me.
Exactly.
Let's look at the data.
You know,
Let's follow the data.
maybe I just show you the data.
The data. But then the reason must be something else.
Well, the reason is his response. The reason is his responsibility.
Let's see the data. Let's see the data. Okay.
So this is the electric field dependence because we also can.
Let's make the window big.
Yeah. Yeah. So the black dots here is the slope. It's about 80 ohm per Kelvin over this range of the electric field. The residual resistivity is the blue dots here. Yeah. So
Oh, come on, one is constant.
Yeah, one is almost a constant, one changes by quite a bit. And this is the case with the electric field. I think we also have something for the doping. For the doping here, that for instance, this we change the doping, not by the electric field, we change the doping in the constant electric field. This is the slope, and this is the residual. I mean, they don't seem to be correlated. Possibly.
You measure the electron density,
Measure what?
that's same states.
What
Density
does
of
the Hall do? And of course, where's the
the Hall density. Yeah, you can actually see that the Hall density jumps by 2 at a 0.98. Yeah, basically, this is where the Van Hoff singularity is, and you do get the maximum residual resistivity here, right?
Okay, then it's a lack of screening or something that you suddenly see your defects much stronger. It's something indirect.
Wait.
Because I mean, in
It's 50 ohm.
No,
This is
sorry, but I mean, there is a strong dependence of rho zero with filling, right? And your
Yes,
defect
because we are
concentration cannot change.
scanning through, and this is the near the location of the Van Hoff, right?
Yeah, so then you lose your screening. So you have much less carriers, and then maybe rho zero is because you have less screening. Something, right? I mean, you need to have a reason why rho zero doesn't behave the same way as the slope. They are related.
We're running out of time. Can we go to one more question?
Sorry.
Yeah.
I need to
Yeah.
I fear I'm going to be much like Silke, but I'm going to question Piers. Piers just said, any squared tau over M. Lovely, if you want that. But that has to apply to the slope as well as the defect concentration and residual resistivity. So if you're going to have a huge variation in rho naught and invoke any square tau over M, then what the hell is with the slope? Piers, I throw it to you. There's the data.
You cannot invoke me against
Look at the data, Piers. Look at the data. Sorry, Piers.
But I think it's. No, really.
No, but it's intriguing. I'm not questioning the data, but there's something scratching at the back of my mind of, it would be interesting to understand this rho naught variation. You know, that to have something to throw. Silke.
You know, the disorder density is fixed,
Exactly.
right?
So.
But we are tuning the density, and
Right.
it goes through a Van Hoff.
No, that's what, but Silke
Yeah.
was trying to help you. Maybe you're losing the screening that is hiding the impurities, and therefore the impurities are more aggressive scatterers near there. I think
Yeah,
that's what.
something like that I
Exactly.
was trying to say.
But this is only a factor of, this is not really a huge change, for instance, here. Okay.
You mean
depends
a
on-
factor of two?
It's a factor.
Oh, look, my rho zero is changing by an order of magnitude,
Yeah,
while
yeah.
my slope doesn't change, right? That's your statement. I
Yes,
guess.
in the other one, yeah, in the electric field,
So
same
so
thing.
you need an explanation for that, because it's totally counterintuitive. It cannot both be argued in terms of change of carrier concentration, because your slope would see that too.
There's
It
something
is in
interesting.
there,
There's
so it
something-
cannot.
No,
work with that
I-
explanation.
Okay,
It
I
doesn't work.
you know, I have no theory for strange metal, but let's say that if I take, I can do an effective mass measurement, you know, not exactly at the strange metal, but slightly away from the strange metal, like what Andy McKinsey did. And plotting that mass is actually a Planckian scattering rate. And what it says is basically that this slope doesn't change. It's almost saying that, you know, that Planckian scattering rate is really.
Planckian is extracted by putting the carrier concentration in, right? I mean, the Planckian scattering and Andy McKinsey's thing, he does a very involved thing. And
Yes, okay.
the carrier
In this case, it's hard to do.
concentration-
In this case, it's near the Van Hoff, you know, except at the Van Hoff, I don't know what density to put in. But in the other case, I know what to put in, yeah. Well, in this case, I don't know what to put in, but in the other case, I know what to put in.
It's the scattering. The carrier.
So I can just say that I don't have any explanation.
That's fine.
You know, well, I never said I had any explanation. The resistivity changes, you know, the residual changes, but the slope almost doesn't. At least there's no correlation.
Interesting, but puzzle.
This is fascinating, and there's something hiding there. It may be trivial once you understand it, but
Mhm.
nature's whispering in your ear here.
On that point, great. I think we'll have coffee. Thank you very much. And wait till we start again.
20 minutes.
Oh, so 10 minutes to 12.
Yeah, so we're running 10 minutes late. After the first one.
Yes.
Yeah, exactly.
It's a really enjoyable conference.
Even when we schedule it,
Yeah.
It's like,
Yeah, let's see.
they're supposed to be